model that he came up with. We're going to go now. I'm currently on slide number 9. The next 2 slides I'm going to jump over and then come back to. So I'm going to go from 9 down to 12. Now, this looks nothing like what the actual Schrödinger model has in it. His equation is like a crazy thing with several, 3 second derivatives with respect to each of the 3 axes, and some energy terms in there, and Planck's constant is in there, but it's Planck's constant divided by 2 pi. Anyway, there's this big mathematical equation that is the Schrödinger equation. And from that equation, all of our the energy of electrons kind of spilled out. This is an interpretation of the Schrödinger model that we can actually wrap our brains around. So if you'll just walk with me kind of through this, a big difference between interpreting Bohr and interpreting Schrödinger, you can understand this, is Bohr would have had electron energy levels as rings. And you saw several of the slides just had these concentric rings, getting farther and farther away, and the farther you got from the nucleus, the higher the energy of electrons were. Schrödinger follows the same idea. However, rather than just the simplistic rings for energy levels, Schrödinger's energy levels broke up into sub-levels. Still, we have the first energy level is close to the nucleus, and then as you go higher in energy levels, we get farther out from the nucleus. But as we go farther out, there are more and more sub-levels, because there's more room for things farther out from the nucleus. So if you'll just walk kind of with me, I don't know what you brought from Chem 1. Our Chem 1 department is kind of finding itself again. We've been given the task of changing our curriculum. Sore spot with me, so I'm not going to get into it because I don't think it prepares students well for this class, and so I'm disappointed that our district is doing this to you. But anyway, I'm hoping that you remember S's, P's, D's, and F's. You did electron configuration in some form. You're saying no.
I barely remember. We did, but I barely.
Okay, all right, and you may not have done F's, and that's possible. But this all comes back from the same source. It's all part of the interpretation of what Schrödinger did. In the first energy level, very close to the nucleus, there's not much room for much. Really, there's just room for 2 electrons. And that would be the 1s. We call it a sublevel, although that just makes up the first energy level. When we get out a little bit farther from the nucleus, we go to the second energy level. And the second energy level is broken up into 2 sublevels. There's 2s and 2p. So the number out in front just corresponds with the energy level that the electrons are. So first energy level is just 1s, then it's done. Second energy level's got 2 sublevels, 2s and 2p. The s sublevels always hold just 2 electrons. The p sublevels can hold 6 electrons. So there's a difference not only in the energy of them, p is higher energy, but p has more capacity. We get to the third energy level, then there's 3 sublevels, 3s, 3p, and 3d. So you see, every time there's an s, then there's a p except for the first one, then there's a d, starting at the third. The d sublevel has room for 10 electrons. So you can get 2 electrons in s, 6 electrons in p, and 10 electrons in d. So every time you go from one sublevel to the next, you can go up by 4 electrons. And so you just keep going like that, and as you see, in the 4th energy level, there are 4 sublevels. In the 5th energy level, there are 5 possible sublevels, and there would be 6 sublevels in the 6th, and so on. Yeah.
Say like an electron is going from energy level 5 to 3. Like you said, it can go like to random energy level, right?
Yes.
Higher to lower.
Yes.
Does it like always go to the lowest sublevel?
Not necessarily. It might go from 5p to 3d. So yeah, those sublevels are distinct from each other. Yeah, and they do within an energy level. The sublevels have different energy themselves. So the S is always the lowest energy sublevel within energy level, and then it just goes up from there. Like D would be higher than P, which is higher than S. Yeah.
But when does the electron like go to different levels?
It can only go to a different energy level if you give it energy. If it's got to absorb energy, jump up higher, and then if you leave it alone, that excited electron will return back down. the home place for an electron is its lowest possible energy, and then only if you cause them to jump up, will they jump up. So you see that there's a little formula over here. This one sometimes does get asked on the AP exam, so I'm going to make sure that I say it to you. If you know what energy level you're dealing with, if you take 2 times that number squared, like in the 4th energy level, 2 times 4 squared tells you how many electrons can possibly be held in there. Let's see. The s orbitals always have room for 2 electrons. Oops. The p's always have room for 6 electrons. They don't have to have that many, but they have room for that many. The d's always have room for 10 electrons. And then f's have room for 14 electrons. Now, if you add all these up, you'll get 32. But this is just a quick formula for us to just keep in our mind. So there is some numerical consistency. Whatever energy level the electrons are in, that's how many sublevels there can be. And if you take the energy level times 2, the energy level number squared times 2, that gives you how many electrons there can be. Okay, now I'm going to take you back and let's see what this looks like. I don't know if I used the term orbital yet, but within each sublevel sublevels are made up of orbitals, which are little regions in space that have room for 2 electrons. And so this is a picture, and that's what it says up there in the title. Orbital shapes, now there's 2 electrons in each orbital. So in an s orbital, whatever energy level you're in, if you're in the s sublevel, there's only 1 orbital. It's got room for 2 electrons. So an s sublevel is spherical in shape. That's not why they call it s. S stands for something different. Of course, something different starts with s too. So the s is not for spherical. There's 2 electrons that are allowed in there. Now let me just make a mention of the fact that there are 2 electrons in an orbital. Aren't electrons negatively charged? Electrons are negative. And don't 2 negatives in the same space repel each other? So how can you get 2 electrons in an orbital? And in fact, you're going to find out as we do bonding, electrons desire to be paired up in an orbital. How can that be if they're electrons and they're both negative and they repel each other? Arjun?
Because of like the lone pair.
Even in a lone pair of electrons, you have a pair of electrons in an orbital, which that orbital is a pretty confined space. Here's what happens. Electrons are charged, right? They have a negative charge. So many coulombs. A charged particle that is in a rotational kind of motion, a spinning charged particle, will create a magnetic field. So within an orbital where there's 2 electrons, 1 electron will be spinning one direction, creating a magnetic field. The other electron in that orbital must be spinning the opposite direction and creating the opposite magnetic field. Now, they are still negatively charged, and they still do push away from each other. However, the fact that they have opposite spins and therefore opposite magnetic fields allows them to cohabitate in an orbital. So in this little tiny, this is the shape. We have an x, y, and a z-axis. It's a 3-dimensional graph if you're in pre-calc or higher. And so that we assume that the origin is where the nucleus is. And so somewhere on that sphere are 2 electrons. And they can exist there because they're in this, one in a positive motion, the other one in a negative spin, and they have those opposite magnetic fields, which allows them to be together. And every time I instruct people on this, it always makes me smile, and I encourage you to try it too. My brain doesn't allow me to take one hand and spin it like an electron is spinning this way forward, and the other one spinning backwards. Do that at the same time. I can't do it. Forward, backward, same time. Forward, backwards, same time.
My brain's too hot for this.
Come on, brain. It's not that hard. Forward.
I can't. I'm too dumb for this.
Well, I kind of. I don't know. Yeah.
It's funny. But electrons can figure it out, I guess, because they don't have the same brain for both of them. If this is 1s, close to the nucleus, the next energy sublevel that would come in would be 2s, also a spherical shape, and it would be above or outside of the 1s. Now, s sublevels are pretty simple because they're only able to hold 2 electrons, so they're a spherical shape. When we get to the p's, I had told you before, any p sublevel has room for 6 electrons, but they're very specifically arranged in this way. There are 3 p orbitals in each p sublevel, as long as we're in a p. P's are always arranged like this. There are 3 p orbitals that are dumbbell shaped. So you have 2 electrons somewhere in this dumbbell shaped region, and you might think, oh, of course, one there and one there. Not necessarily, they both might be over there, they both might be over there, or you might have one in each. Somewhere in that shaded region, there's 2 electrons that can be. And then perpendicular to this one, like coming out of the board and into the board, this is a projection that makes it look kind of funny, like it's off on an angle. It's not on an angle. These 3 are all perpendicular to each other. Like when they're put together, it looks like this. And you can kind of get the sense of all 3 perpendicular. So 2 electrons in there, 2 in there, and 2 in there. And that adds up to 6 electrons. So a p sublevel is made up of 3 p orbitals, each allowed to have 2 electrons in it. The d's and the f's are bizarre. They're wacky. The next slide has the d's and the f's. There are 5 d orbitals possible. That was why the d has room for 10 electrons, is because there's 5 d orbitals, each allowed to hold 2 electrons. So when we look at the d's, this wacky set of 5 different shapes, all 4 of them are the same shape, and then we get to this last one. Yeah. Yeah. 4 parts, 4 parts, 4 parts, 4 parts. I mean, there's all of our d's. And then we get to this. What is that doing there? But that's a solution to the Schrödinger equation. And he came up with that. So, and this is bizarre because you see 4 parts to each of these and you think, I thought orbitals can only hold 2 electrons. Yes, 2 electrons somewhere go in there. Why are there 4 parts? Well, this is not like some architect designed it. This is the way that that orbitals, according to the Schrödinger model, the way that they go into atoms. So this entire thing, 5 d orbitals make up a d sublevel. Then this. The F is crazy bizarre. And keep in mind, each of these purple regions is room for 2 electrons. So this whole intricate, crazy looking thing has room for 2 electrons in it somewhere. Where are they? Well, they're somewhere in that purple shaded region. So there's 14 electrons that are possibly held in F because of 7 F orbitals. Yeah?
Are we doing anything with G orbitals?
We will not.
Oh my God.
No.
I just want to see what it's like.
It's literally.
Yeah, I don't know.
Stop flexing, John.
Did you look up D's or G's?
No, it's on the dunks thing.
Not to talk about the H orbital.
Oh, on this thing, yeah, I did mention that G is possible. If you're in the 5th energy level, you should have 5 sublevels, S, P, D, F. And then after F, they just start going alphabetical. Then G, then H, then I, like that. But those are just theoretically, yeah. They are just theoretical. Our periodic table only goes up to F. We don't have enough elements. We'd have to get another 20 or so elements to get into the G's. Maybe not that many. Let's see, what would we be through? We're through the 7th row. That takes us to 7P. And then we would get into, let's see, the first time we would have a G is in the 5th energy level. Yeah, we wouldn't even need 20 more elements that we would get, but we're not there yet. Got a question, or you just? It is confusing, I know. And I'm kind of sour because we used to cover all this in Chem 1 thoroughly. And now, many of our teachers just hand wave and don't really cover it. Oh, yeah.
I think you can just like show us an orbital chart and that's it.
I just like nodded and smiled my way through the chapter, to be honest.
Now, have you seen this?
Oh, yeah.
Yes. Yeah.
Some yes and some no is okay. And if you're I'm going to try to walk you through this. This gives us the order of the energy sub-levels. I took the energy levels and color-coded them. First energy level is this red color, deep red color. Then the second energy level is green. Third energy level is blue. Fourth energy level is like a burgundy kind of red color. Fifth energy level is pink. And notice, at the beginning, when everything is simple, it's what you would expect. First energy level, and notice the arrow. Energy is going up the higher we get. So down here at the bottom is lowest energy close to the nucleus. 1s is close to the nucleus. Then we have the second energy level. Look at that, 2s and 2p, second energy level. It's got two sublevels in it. Third energy level is where it starts to get goofy. Look, 3s, 3p, and then there's an intruder. Before the 3d, here's the 4s. What's that intruder doing there? Well, it turns out that the D sublevel is so much higher in energy that it actually overlaps the next energy level's S. So we don't get 3D, we don't get 3D in there until after 4S. Now the same thing happens in the next, so in the fourth energy level, you don't get 4D until after 5S. See how 4D is higher than 5S? That's always true. The F sublevel, once you get to the fourth energy level, there's 4S, 4P, 4D, and 4F. The Fs are so high in energy that they'll overlap the S that's 2 energy levels higher. So you won't see 4F until after 6S. There's 6S, above it, 4F. Now I didn't go up any higher than this. If I went up to 7S, it would be 7S and then 5F. And then 4D. No, 6D. Because the D's overlap the S that's 1 higher than them.
What do the lines?
Okay, so now I was going to talk about that. Each of these lines, notice all the S's have 1 line next to them. The P's have 3 lines. The D's have 5 lines. That corresponds with 3 p orbitals. So there's 3 lines. Each line represents an orbital. The D's have 5 orbitals, so they get 5 lines on that energy diagram. Now, what we use this thing for is we use this to represent how the electrons are arranged. If I ask you, well, how are the electrons arranged in, I'll use something simple, lithium, 3 electrons. Electrons will always fill into an atom closest to the nucleus and then out. So you always start with 1s at the bottom. It's close to the nucleus. So with 3 electrons, lithium has its first 2 electrons in 1s, and we represent electrons with arrows. Remember how I was talking about positive spin, negative spin? Up arrow is one direction spin, down arrow is the other direction spin. So we assume like up is positive 1/2 and down is negative 1/2. Oh, never mind the 1/2 part. There's something called quantum numbers, which we're not doing. They took that out of the AP curriculum, so never mind the 1/2 part. So anyway, there's the first 2 electrons in lithium, but it has 3. 1s is already full. It's got room for 2 electrons. Each of these lines that are in orbital, 2 electrons only. So you get an up arrow and a down arrow on a line, that's it. On the 2s now that 1s is full, we go up to 2s, and that would be the electron arrangement in lithium. Arjun?
What does it mean when the arrows is like going from 1s to 2s and from 2s to 2p? Or just is it not?
They're not pointing to things.
Yeah,
They just show the up spin or the
Yeah, the electrons are being represented with arrows because one electron in orbital has to have the opposite spin as the other. So they represent that with the direction of the arrows. That's all.
So it's not going to the.
It's not pointing at anything. Yeah. Eddie?
Why would it be an up arrow?
We just so that everybody always does the same thing. We put the up arrow first. It's just as correct if you put the down arrow, but the convention is that everybody puts the up arrow first. Doesn't really matter. It's not. I mean, an electron is going to have a spin. We don't necessarily know if it's positive or a negative. Rhea?
I was going to ask the same thing. So if there's only 1 electron
Make it up. Yeah, put the up electron first before you pair it up with a down. Yeah.
Why is there only one up? Wouldn't there need to be like a down to like balance it out or something?
No. For lithium, this is one of the things that makes lithium so reactive, is it's got this unpaired electron. So this is the electron arrangement of lithium metal. This thing is what makes lithium reactive. That's why you put lithium into water and it catches on fire and blows up because of that.
So like if anything has like an odd number, would it?
Yeah, if it's got unpaired electrons, it's probably reactive. Yep. Yep.
Is that why the alkali metals are so reactive?
Yep. Because they only have one s electron. That's exactly why. Yep. Okay, so another thing that I wanted to show you, I know we're going to have to wrap up. So we always fill electrons from 1s and then upward. When you get to the sublevels that have more than one orbital in them, so far we've just done things with s's. If I go to carbon, number 6, here's my first 3 electrons in carbon. Number 4 is going to pair up in 2s, like there. There's 4 of my electrons. And then electrons number 5 and 6 for carbon are going to look like this. The number 5 goes there. Now we have a choice. Number 6 can pair up with it and go down, but that's not what happens. We're going, when we have multiple orbitals, put 1 onto each before they pair up. So this is the electron arrangement for carbon. Now remember, I told you that within an orbital, electrons are spinning, one positive, one negative. They're going to have the ability to stay together. However, that doesn't necessarily mean that they are that's their first choice, is to pair up. What that means is that they are still negatively charged, and they will try to spread out as much as possible if they have that option. So your first 3 electrons in a p sublevel will always go up, up, and up before you make any pairs. Now, if I asked you for the electron arrangement of oxygen, oxygen is 2 more than carbon. Carbon is 6, oxygen is 8. If I have to put 2 more electrons onto here, then the number 7 electron will go there, and then number 8 electron will go there to pair up. So we'll have a pair of electrons and then 2 unpaired. So this would be the last electron that I drew. Yes, Sergeant?
When you add like an extra one and you have to pair it, doesn't matter which one, or should you just put it on the first?
Always start from left and go right. That's always the way everybody does it. Biggie?
Is that why double gases are so perfect? Because they got no
They've got no unpaired electrons. Yep. Yep.
except the
Double gases.
I'm going to just go ahead and wrap this up for today. I do want to mention, though, it is pretty amazing that Erwin Schrödinger came up with this model of how much energy electrons have. We interpret Schrödinger's model using this. You're going to see tomorrow, this arrangement of electrons corresponds perfectly with the periodic table and the arrangement of elements on the periodic table. That periodic table was developed around the year 1908, 1910 or so. The first decade of the year 1900, the 1900s. Schrödinger came up with this like 15 years later, but it turned out that his theory, Schrödinger wasn't paying attention to the arrangement of things on the periodic table, but his theory lends itself perfectly to the arrangement of elements on the periodic table. Perfectly. It really, when I first saw this, and we were doing it in physical chemistry in college, I thought, man, this is like the perfect model in science. It just fits so well with what had already been experimentally observed. This is not really experimental observation, it's just theoretical. But man, it sure fit. Does that mean that Schrödinger was right on everything? Nope, it doesn't mean that. We haven't figured out anything that's better than what Schrödinger said. I mean, 100 years later, we're almost the 100th anniversary of Schrödinger's paper that he published. Still is the leading, theory on atomic structure. Yeah.
Where does T even like the G sublevel even go on the periodic table?
Yeah, we would have to have something inside of the F's. So yeah, the F, these 14 F elements would go right here. So the periodic table would be 14 more elements long if we put these 2 rows up into there. And then the G's would have to go between S and the F's. So yeah, it would make the periodic table. Put the F's in there would make it much longer, and then putting in the G's in there would even extend it more. It'd be very obnoxious. Yeah. John, you might be the one to figure out an element that's got a G electron. Yeah, that would be good. And all of us could think, oh man, I made that fun of that guy when he was in high school.
How many homework problems do you think we can do?
You can do quite a few. There's a bunch of them that involve the light equations. C equals lambda nu and then E equals H nu. So, yeah. Get started on those and get those out of the way. After tomorrow, you'll be able to do a bunch.
No.
But yeah, start some today. Trust me. All right, so that's all. We'll pick this up tomorrow.
Sister Mark.
Yeah.